I'm Meredith Lucky, a VP of Sales at CAST, and I'd like to welcome you to CAST webinar on CPU subsystem total power consumption. Our speaker today is Dr. Nikos Zervas, CAST's Vice President of Marketing. Nikos holds a PhD in low-power design methodologies, and he's addressed power issues with many CAST customers over the years. Information he would like to share with you today. Nikos was an early pioneer in semiconductor IP, co-founding Alma Technologies and developing some of the first image compression cores over 10 years ago. Since joining CAST in 2010, he has expanded his technical expertise to processors and system integration and has helped many CAST customers make successful processor IP choices. So Nikos, let's begin.
Thank you, Meredith. So today's webinar is about power and energy consumption of processor IP cores. So first we will explore what it takes to make an apples-to-apples comparison of power ratings between different processor cores. And then we will discuss why power ratings do not provide much information about the energy efficiency of processor cores. We will see that energy efficiency is mostly a matter of a processor's performance, of a processor's area, its code size, and its ability to support dynamic power management. So when it comes to selecting a processor core, one of the first things most people would do is to check milliwatts per megahertz ratings or microwatts per megahertz ratings. Milliwatts per megahertz is similar to miles per gallon ratings for automobiles, but it's much worse in many ways. In the miles per gallon case, there's no standard driving cycle and there's no real-life city or highway mode of driving. In a similar way, milliwatts per megahertz can vary significantly depending on the target technology process, on the cell library, on the operating conditions, on the technology mapping optimizations, on the toggle activity, practically the software that the processor is running, and the actual tool flow. In a quest for low-power processor, you would find data like those in this slide. Some vendors would not provide power data at all and just say low power or the lowest power. Some would give you a figure, name a geometry, and some others would list some power simulation parameters. So with a first look, it becomes pretty evident that getting consistent ratings can be a real challenge. Just to give you an idea, a design mapped on a general purpose library can consume 50% or more power than what the same design would consume when optimized in the exact same way, using the same tools, running the same software, but being mapped in a low power library of the same geometry that uses high voltage threshold cells. Then experienced designers know that optimization options can make a huge difference. For example, optimizing a design for speed and setting the frequency, the clock frequency goal to a relatively high value can result in a power consumption that is 50% or even more than the power of the same design when optimized for either area or power, and when we set the clock frequency target to a relatively low value. Something that is many times overlooked is the activity statistics. The power of any processor heavily depends on the software that the processor is running during power simulation. For example, power while the processor is only using the register file and the ALU can be much smaller than the power while the processor is accessing the memory and using the floating point unit. So comparing the alternative processors running the same software and mapped on the exact same technology using the same tools is essential. Last but not least, someone needs to check the footnotes of published numbers to see what configuration of the processor do the power figures correspond to. You need to be checking the power of the configuration that you plan to use. And then you also need to check whether vital modules have been excluded from power simulations like clock trees, register files, etc. Bottom line is that you need to compare power ratings for your design and your design constraints. You need to ask your alternative vendors to provide that, because it is more likely that you would not find what you need on the web with a simple search. Now, even if you get your milliwatts per megahertz ratings consistent, you're not done. Let's go back at our school years and recall that power is just the rate at which energy is consumed over a small period of time. Energy, not power, is what gets consumed. Energy is what batteries store. Energy is what counts. Therefore, energy efficiency is what people are looking for their low power designs. Milliwatts per megahertz would tell you very little about the energy efficiency of any given processor. As we will discuss in the following slides, a processor energy efficiency depends on performance, area and code size of the processor, and its ability to apply power management. So let's take a look at those in more detail. Some people may find this surprising, but faster, more powerful processor can actually be more energy efficient. And this is because higher performance allows doing more in less time and sleeping for longer times. So in practice, that means that a more powerful processor requires less energy to complete a given task. Alternatively, higher performance can be used to operate on a lower clock rate. And when you operate at a lower clock rate, you get a reduced power for your clock tree and the CPU. Also, with a lower clock frequency, timing closure is easier. And that allows to synthesize in a smaller footprint and use high voltage threshold cells for all your design, for 100% of your design. Both those decrease leakage power. So again, faster processors can be more energy efficient. Let's look at a couple of examples to understand this in a bit more detail. In our first example, we consider an application that requires the processor to deliver 100 DMIPS in 1 second and then sleep. We consider three different processors: the ARM Cortex-M0, the ARM Cortex-M3, and the BA22, which is a 32-bit processor offered by CAST. With a first look, the M0 seems to be the more energy efficient one because it has a lower milliwatts per megahertz rating. But it is not as powerful as the other two. Actually, when we calculate the clock frequency that we need to run at so that we can deliver the 100 DMIPS in 1 second, it turns out that the BA22 needs only to run at 58.82 megahertz, while the Cortex-M0 at about 102 megahertz. As a result, the energy to complete the specific task, and the energy is just the product of time times power, is significantly less for the BA22, regardless of what the milliwatts per megahertz ratings originally indicated. On our second example, we consider an application that requires the processor to run at 50 megahertz. So now we cannot tweak the frequency and need to deliver 200 DMIPS as soon as possible and then sleep. We're again considering the same 3 processors. Now the clock frequency is the same for everyone, but the higher DMIPS megahertz of the DMIPS of the BA22 makes it complete the task at a much smaller time. So as a result, the energy to complete the task is again smaller, regardless of what the milliwatts per megahertz ratings would indicate. So we've got a parameter that we need to keep in mind, and this is the performance of this processor. Another parameter that affects the energy efficiency is area. An area is important when we've got an application with short active periods and long idle periods. In such a case, the idle or static energy can be equally or more important than active or dynamic energy. And the way that area affects the static energy is through leakage, and leakage currents are proportional to area. Here we have a graph that of cell area versus leakage power for designs mapped on TSMC 90 nanometers technology. That proves the point that area is proportional to leakage power. So smaller processors can be more energy efficient. Let's see an example on how that works. In this case, we consider an application that requires the processor to run at 10 megahertz and deliver 100 DMIPS every day. So in our example, we consider a small processor and a fast processor. Our small processor is the BA22 without the multiply and divide unit, and the fast processor is the BA22 with the multiplier and divider unit. So the small processor has a lower active power and a lower static power, but the fast processor has significantly higher performance, DMIPS megahertz. So in the same way that we've seen in our previous example, the fast processor ends up requiring less energy to complete this specific task, to provide those 100 DMIPS. But when we look at the full picture, when we look at the energy over 24 hours, it turns out that the small processor consumes much less energy. So here we've got a second parameter when we consider energy efficiency of processors, and this is area. The next question that we need to ask ourselves is whether we need to focus on just the CPU or the CPU and the memory. And the memory's power and energy is to a great degree defined by the CPU, because the CPU runs code, fetches code from the memory. In this slide, we compare typical numbers, power consumption numbers for a CPU, a 32-bit CPU on a 90 nanometers versus power consumptions of different types of memory. So a typical 32-bit CPU on 90 nanometers running at 100 megahertz would consume about 5 milliwatts when active, and its idle or static power would be in the order of 0.01 milliwatts. A 32 kilobytes on-chip SRAM, which could be the memory where we run code from on an embedded system, on the same technology and access at just half the operating frequency of the CPU, would consume 9 milliwatts, so significantly more than the CPU itself. And its idle power, depending on how fast it is, could be in the order of 0.02 to 0.06 milliwatts. Now, in one-time programmable and OTP memory on the same technology that we don't access that frequency, so we're making the assumption here that we would only run it at 10 megahertz, would have an active power of 5 to 50 milliwatts, so up to 10 times more than the actual CPU. And the idle power for OTP is about 0. Where it gets really ugly is when we consider external memories. In this case, we consider a low-power DDR, 256 megabits, and the active power of that is something in the order of 180 milliwatts, so 30 times more than the actual CPU. And the idle power, depending on whether the memory is on standby or idle mode, can be either 3.5 milliwatts or 0.01 milliwatts. So focusing just on the CPU is like losing sight of the forest for the trees. And when we talk about memory, we're actually talking about code size, because this is how the CPU affects the memory. And smaller code size means a smaller instruction memory. So that means lower energy cost per access. Smaller code size means that we need fewer instructions to complete a specific task, so fewer memory accesses for that specific task, and therefore lower energy. And something that might not be too evident is that smaller code typically means a better I-cast behavior. And a better instruction cast behavior means fewer accesses to the central power-hungry memory, which could be a DDR memory, SDRAM, NAND flash, or whatever. So code size efficiency means energy efficiency. And let's look at an example on code size and energy. In this example, we consider low power processor A, which consumes 3 milliwatts, and processor B, which consumes 5 milliwatts, so more power than processor A, but it's code efficient. It's code efficient. So it produces 50% less code for the same application. If our system would consist for just the CPU and a static RAM, a non-chip static RAM, then and if that code would be 64 kilobytes, then the processor A would consume about 13 milliwatts, and that is based on the assumption that the code will be 64 kilobytes and that the memory will be accessed at 50 megahertz. Now, with processor B, because it produces 50% lower code, the size of the on-chip SRAM could be half, could be 32 kilobytes. And therefore, the energy consumption or the power consumption of processor B plus its memory would be 10 milliwatts compared to 13. So we see that the code-efficient processor B ends up actually being also power efficient as compared to the originally lowest power processor A. Now, if our processor would access the code from a DDR, and we make the assumption that this DDR would be accessed at 30% of the time, then with processor A, we'll have 53 milliwatts, while with processor B, with a smaller code size, 50% lower code size, we would access that DDR at half the time because we need to fetch half the code. So it would be active, the DDR would be active at 15% of the time. And that will result to 33 milliwatts compared to 53. So now we've got a third parameter on top of performance area, and that's code size when we think about energy efficiency of processors. One last thing to consider is dynamic power management. Dynamic power management techniques are used in almost every low power design to reduce energy consumption by orders of magnitude. Processors with few more milliwatts per megahertz can automatically gate clocks to unused modules. So let's say they would clock the floating point unit when it is not used, or broadcast the idle or active state of its major units and provide means to externally gate their clocks. And some processors would even allow software control over the CPU and the bus's frequencies so that you can adjust the clock frequency to, let's say, the battery level or the processing requirements of the application. So let's put all those together. When you compare different processors and you are looking for the more energy efficient one, you can go the easy way and compare milliwatts per megahertz ratings, or you can go the right way. And the right way imposes that you profile your application needs and weigh active versus idle power. You need to assess the energy impact of processing power and area. You need to take into account code size and memory energy and make sure there are no roadblocks to dynamic power management. Regardless of what you decide to do, you need to work with your vendors to characterize the processors for your application. And if you decide to do an exercise like that, the BA22 from CAST is a processor that you need to take into account. And that's because BA22 is energy efficient in all of the aspects that we have seen. It is powerful. It provides 1.7 DMIX per megahertz. It provides extreme code density. It is relatively small and low power, so its milliwatts per megahertz ratings are pretty competitive. And it supports advanced dynamic power management features like automatic clock gating, separate clocks for its main units, and status broadcasting, and allows also software-controlled frequency scaling. And if you decide to learn more about the B22, you can visit our website. You can evaluate the code size and speed of the B22 using one of our development kits. And you can contact your local representative or a CAS salesperson. The details are provided in this slide. And these people would make sure that you get support from experienced designer to characterize the B22 for your design. With this, I would like to thank you for your attention. We would now move on to question and answers. So, Meredith?
Okay, thank you, Nikos. Yes, thank you. That was very interesting, and we have a few questions from the attendees. I'll go through all of the questions. The question is, you described how milliwatts per megahertz ratings can tell us little about the energy efficiency of a processor. How about DMIPS per milliwatts then? Isn't that a good metric to compare processors?
Okay, this is actually a good question. DMIPS per milliwatt is a better metric than milliwatts per megahertz, but it still does not capture the impact of area, code size, and ability to apply dynamic power management. So if you rely on DMIPS per megawatts to choose your processor, you may still be missing a lot.
Okay, then the next question would be, you said I need to profile the processor using my application software. What if I do not have that ready by the time I make a decision? So just to repeat again, if I need my application software to profile the processor, what happens if I don't have it ready by the time I make a decision?
Okay, in that case, using a benchmark representative of your application category or the application software of a previous project would be the best way to go. What you really need to be doing is to use some software that would exercise the same modules of the CPU that you plan to use, that your final application would also use. So, for example, if your final applications heavily use floating point calculation, you need some benchmark that would exercise that.
Okay. The next question is, let me see, is it possible to put the CPU in a sleep mode from software and wake it up? Or is this attained by slowing down the clock to a very low value? And again, just to repeat, is it possible to put the CPU in sleep mode from software and wake it up, or is this attained by slowing down the clock to a very low value?
Okay, I don't know whether that question applies is for the B22 or a general question. I would answer the general case though. Both are feasible with many processors. What happens, for example, and I would jump to the B22 now, with the B22, is that you can use the software to put the CPU in a sleep mode, and then it would be waked from an interrupt that would come through a timer that keeps running or some external source. And independently of that, you can actually have software control over the frequency, the clock frequency of the processor and the buses. So you can do both. The question is whether your processor allows you to do so without too much pain.
Okay. The next question says code density relies on the software developer, doesn't it? Again, I guess this is referring to your slides about how code density affects power. The question is, code density relies on the software developer, doesn't it?
The code size for your application would be determined, of course, by the skills or how much of a good job would the software developer would do. But there's a lower limit set to the code size that relates to the actual instruction set that you're running. So for the same, let's say, software skills, some instruction set would allow you to go up to, let's say, 160 kilobytes, and some other instruction set would allow you to go down to 100 kilobytes or even less. So the end code size is a result of two factors: the instruction set itself and the skills of the software developer.
Okay. The next question is, what are the different memory module sizes that are supported? So I guess this might be a BA22 question asking what are the different memory module sizes that are supported?
Well, the BA22 has a 32-bit address space for data and 32-bit address space for instructions. That allows you to actually, and there's no constraint on what type of memory you can attach to either bus. You can have those buses combined too. So the address, you can hook anything you want to those buses as long as you don't need more than 2 in the power of 32, which is big. More details can be found in the spec, and if I'm missing some part of that question, please send me an email and I will follow up.
Okay. And I think this is our last question. How do you qualify the compiler tools for the BA22? What test suite do you use for it?
How do we qualify?
How do you qualify?
Okay.
Yeah.
Mm-hmm. So the compile tools for the BA22 are based on GCC. Of course, we have to port the GCC on the BA22. The way that we qualify that is by running through a large set of benchmarks and applications that we have. I'm not familiar with the full details of what the compiler guys do, but if it is of critical importance, we could follow up with more details.
Okay, and we did get another question. Oh, they're just coming in now. Assuming a less skilled software writer has access to the code space, would a less efficient processor with lower code density ultimately provide lower power?
I'm not 100% sure that I'm following this question. I would say that for the same skill set, more dense instruction set that provides higher density would give you better results. So if we take the skill set of the software developer as common along different instruction sets, so then the instruction set would make a difference. To be fair, it's a combination of the instruction set and the compiler. So, but when we refer to instruction set, we typically include the compiler to the ability of the compiler to take advantage of the instruction set features. I hope this answered the questions.
So I guess with that, we will conclude the webinar and thank all of the attendees for their participation. We will be following up. Feel free to also send any questions to either Nikos or to enter the contact button on our website, and they'll come to sales, and I can address them along with our processor engineers. Okay, thank you very much.
Thank you very much.